look at some other, I guess, quote unquote complications of the ideal gas law. There's not much. I promise you, it's all a variation on the theme, right? It's all you using PV equals nRT, PIV nRT. So Dalton's law of partial pressures. So this is something that, again, it's a thermodynamic thing. If and when you take thermodynamics, you'll discuss partial pressure. When I took thermodynamics, when I taught thermodynamics, there are complications with this particular law. This law is very simple, but it is not necessarily true physically. It just doesn't work this way because there are interactions between gases. But it assumes it doesn't. That they don't have anything. All right. So what happens when I mix two gases together? Okay, so from an ideal gas point of view, they don't interact. Gases do not interact with one another, meaning that they should have the same temperature before and after. Nothing will change the temperature because nothing really happened. They're ignoring each other's existence. Nothing happened. Okay? Each individual molecule has no volume. So it's also going to stand to reason that they're going to not see one another. They're not going to have their own individual volumes. Well, then if I'm putting them both into a 1 liter container, then the volume of the both of them will be 1 liter. They won't care about the other. It doesn't matter. Right? So if I take helium and oxygen and nitrogen and whatever you want, a whole bunch of gases, and I put them all into a container of 1 liter, the volume will be 1 liter. Okay, and that makes sense also because they're not really interacting and they're trying to expand to fill the volume of the container, blah, blah, blah. So that part makes sense, and I think it doesn't really break down much when we're dealing with interactions. But the temperature would probably change when you mix things, but we're going to pretend it does not, okay, from a point of view of ideal gas. All right? This is one thing that I will say, though. Each gas ignores the existence of the other gases, so each gas will exert a pressure as if the other gases aren't even there. Okay, so what you could do is pretend if I'm mixing gas A, B, and C, if I'm trying to find the pressure for each one of these gases, I'll just use P equals nRT for A, P equals nRT for B, P equals nRT for C. I'll ignore the fact that the other ones are there, and I'll just solve each one individually, and I'll find that each one of the pressures is going to be different. It's not going to be the same. Each gas will exert its own pressure. They will all collectively have the same temperature. They will all collectively have the same volume, but they will each exert their own pressure. That pressure that they're exerting is known as a partial pressure. And Dalton, one of his contributions, he said that if you were to add up the pressures of each of the individual gases, these partial pressures, if I were to add all the partial pressures up, I will get the pressure of the entire container. Okay, so whatever the pressure is in this bottle. So if I were to throw a whole bunch of gases into a container and put a screw top on top and I just screw them all together, they will exert a pressure. They will have an additive pressure together, and I can calculate that from PV equals nRT, each one individually. Okay, so I think that if we were to do an example, it would make the most sense into like what the hell I'm talking about. So let's look at that. Okay, I'm going to look at an example here when I am mixing oxygen and nitrogen. So it's sort of like air, but not specifically air. But, you know, I'm not even talking about the number of moles, so maybe it is air. So I have a 1 liter sample. So imagine I have a bottle of oxygen. You know, like you drink the Coca-Cola out of a 1 liter bottle and you replaced it with oxygen only. And it is at 300 K. So I don't want to do unit conversions right now, so I'm just going to give you the K. So it's about room temperature, 300 K, and 1 ATM. So I'm just letting you know the initial state is 1 ATM. Okay. I also have a half a liter. So maybe I have a smaller bottle of nitrogen. It's also at 300 K, That's not very legible. N2. And it is also 1 atm. So they both have the same temperature to begin with. They both have the same pressure to begin with. This one is double the volume of this one to begin with. Okay, just so you know. All right. Now I'm going to mix these two into another container, a third container, into a 1 liter container. Or maybe if I want, whatever you want, it doesn't really matter. I guess it's the equivalent of me putting this sample into that space. Okay, so imagine I took bottle 2 and I poured my nitrogen into the bottle 1 where oxygen existed. All right, whatever. Or maybe I poured them in both into a third bottle that was 1 liter. Whatever you want, how you want to think about that. It's the same thing. Okay, so my questions are going to be as follows. 1, what's the final volume? So I'm going to final volume of oxygen. What's the final volume of nitrogen? Okay, before I even go on, they don't care about one another. They don't see one another. They don't really care. Gases expand to fill the volume of the containers where they're in. So it is 1 liter. They're both in a 1 liter container. They don't care. They're both 1 liter. Great. So that was simple. Now I want to know the temperature, the final temperature of oxygen, and the final temperature of nitrogen. Okay. I also mentioned when you're mixing two gases, they will both have the same temperature at the end. Well, they both started at 300 K. They didn't get heated. They didn't get cooled down. Nothing happened. So they should stay at 300 K. So they're both 300 K. Now, from a thermodynamic point of view, is that true? No, it is not true. But I won't worry you here in this course. You don't have to worry about that. But when you take thermodynamics, you will see this thing called heat of mixing, and it messes around with volumes and temperatures and pressures and everything like that. All right. So number 3, I want to know the pressure final for oxygen, and I also want to know the pressure final for nitrogen, and I also want to know the total pressure inside that bottle. What are these? Okay, so I want to know about the pressure. Pressure is not as simple. It's not just like look at it and you get it, but it's not hard. It's just using PV equals an RT for each one individually. So I will use PV equals an RT for oxygen. I will use PV equals an RT for nitrogen, and I'll pretend the other one doesn't exist to get these pressures. That's how I'll do it. Okay, so we'll use this as two separate problems. They're fairly simple. Now, I'm not talking here, I'm talking about two states. I'm starting my oxygen, to remind you, I'm starting at 1 liter, 300 K, 1 ATM, and I'm mixing something in, and I'm coming up to a second state. So I'm going from one state to another. So for oxygen, I will have a P1 V1 divided by P2 V2 is equal to T1 over T2 for oxygen. And I will also have that for nitrogen. Okay, and it'll be a little bit different number-wise from one another, but it's the same idea. T1 over T2. All right. I gave you all the units. You don't have to convert. You don't have to worry about it. All right, it's wonderful. It's easy that way. All right. So if you look at the problem statement for oxygen, I start at 1 ATM and I end at, well, I don't know. I have to figure that out. I start at 300K and I end at 300K. I start at 1 liter and I end at 1 liter. So I'll go here and I'll just substitute all these values in. I start at 1 ATM. My first volume is 1 liter. I don't know my second pressure, is what I'm looking for. And my final temperature is going to be 300K. And if I were to solve this right now, oops, I messed it up. I'm so sorry. Here I have the final volume here is 1 liter. I'm sorry about that. This thing is equal to T1 over T2. T1 is 300K, T2 is 300K. And if I were to solve here, the K's cancel, that's nice, the liters cancel, and I'll get ATM. If I were to solve for P2, my P2 for oxygen ends up being 1 ATM. Makes sense, I didn't change anything. If this is the same, this is the same, that's going to be the same. So that's how that would work. So I have P2 for oxygen as 1 ATM. Great. If I'm looking at this guy here, I start out for the pressure for nitrogen is also given to you, the initial pressure, as 1 ATM. My initial volume here was 1/2 liter. My initial temperature was 300K. My final pressure, well, that's what I'm looking for. My final volume is 1 liter, right? They both got mixed into a 1 liter bottle. And my final temperature is also 300K. And so my P2 here is going to be 2 ATM. So this is the final temperature of nitrogen. That's this. Okay. This is my final temperature for oxygen. That's that. And I want to know the total pressure. Well, that's Dalton's law. The total pressure is the sum of the individual partial pressures. So my total pressure here, that's right here, it's simple. P total is equal to P1 plus P2. So it's 3 ATM. 1 plus 2. That's it. And that's the idea behind partial pressure. Okay? So hopefully that made sense. And it just kind of reinvigorates the whole idea that gases don't really care for one another. They don't interact with